Welcome to the last topic of the course. Previously, we've been proving equations involving programs, but that ties us to being a bit too much like maths and it restricts what we're able to say. So in programming, we want to be able to say things like this list is sorted, or this tree satisfies the data type invariant to be a binary search tree, or the inputs to this function satisfy the function's precondition, things like that. So sometimes you can say that kind of thing as an equation, but often you can't. Remember way back in week 6, exploration 2, I told you about propositions, which are things that it makes sense to try to prove. So for example, when I write prove P implies P, then P is a proposition and P implies P is a proposition. And when I write an equation like n plus 0 equals 0, then n and 0 and n plus 0 are not propositions, they're natural numbers, but n plus 0 equals 0 is a proposition. So what we need is a way of introducing new propositions. And the way that I introduce a new proposition is by explaining what are the possible ways to prove it. So as well as introducing new propositions, we now also have a way to introduce new proof rules. So let me show you the syntax. I'm going to write the proposition that says that one natural number is less than or equal to another one. The new keyword is prop, which says that we're defining a new proposition. And I'm going to write L-E-N-N. And this says that this is a family of new propositions with two parameters, both of which are natural numbers. So LE with two specific natural numbers is going to mean the proposition that the first one is less than or equal to the second one. Now I'm going to write where, and now I have to list all of the ways that I want it to be possible to prove that one number is less than or equal to another one. So first of all, I want to say prove LEZN, because I want it to be possible to prove that 0 is less than or equal to any other number. And because I'm introducing a new proof rule, I need to give it a name. So I'm going to say by LEZ. So LEZ is going to be a new proof rule that we can use to prove things that look like this, that 0 is less than or equal to some other number. So if I stop now, then I can prove that 0 is less than or equal to anything, but there are a lot of other true inequalities about natural numbers that I can't prove. So I need another rule, and the other one is going to say prove LE successor of M, successor of N. So prove that a successor is less than or equal to another successor. And I'm going to name this rule by LESS for named after the two successors in it. But I don't want this to be always possible to be used, because if I left it like this, now I could prove, for example, that 3 is less than or equal to 2, because they're both successors. So I'm going to say where, and now I can introduce subgoals that you would need to prove in order to use this rule. So I can now say as a subgoal, prove LEMN. So now what this means is that I can use the proof rule LESS to prove this as long as a subgoal I prove this. So it turns out that this really captures what it means for one number to be less than or equal to another number. So this makes it possible to prove the inequalities that are really true, and I can't prove the ones which aren't true. But from ASK's perspective, this really is the definition of less than or equal to on numbers. So all ASK knows is what I just told it. So let me show you that we can prove that, say 2 is less than or equal to 3, like this. Now, this is a pair of successors, so I should be able to prove this using by LESS. Now, when I send this, ASK is going to reply and says, yes, I can prove it this way, but I must prove that 1 is less than or equal to 2. And now we're in the same situation, so I can say the same thing again. And now ask says, yes, but I must prove that 0 is less than or equal to 1. And this time, so now if I say by LESS, if I make a mistake and send this won't work because this rule doesn't match the situation I'm in because 0 is not a successor. So instead, I can prove this by LEZ. Now ask will accept this and it changes to proven. So I can combine this with all of my other proof tricks. So I can say, for example, prove that n is less than or equal to n. And I'm going to say, I can prove this by induction on n. So I'm going to say inductively n. And I'm going to say from n. So now I'm saying from a natural number. So like usual, I've split into two different cases for the two different things that a natural number can be. And in the first case, I have to prove that 0 is less than or equal to 0, which I can prove by LEZ. And in the second case, I have to prove that successor of n prime is less than or equal to successor of n prime. So I can prove this by LESS. Now, this is an example where the sub-goal, which I said that you have to do for the LESS rule, is actually handled automatically by ask, but I can add it back in. This should be where prove LE m prime m prime. And this is exactly my induction hypothesis. So I have this by given. Okay. Let me show you another example. Oh, by the way, a thing I should mention is this can be infix. So I can say like this, like this. This works just as well. Yeah. So this is now exactly the same, except that I'm writing it infix. So if you have two natural numbers, then putting a less than or equal sign between them makes it into a proposition. Okay, let me introduce lists. Is empty or a fix cons. Now I want to write the I want to write the proposition that says that a list is sorted. So it turns out to be a little bit tricky to do that directly, but I can do it if I first define something a little bit stronger, which is that a list is both sorted and all of its elements are larger than some other number. So I'm going to call this sorted bounded. And I'm going to give two parameters. First of all, a number, and then a list of numbers. And I'm going to say where. Now I'm going to say that the empty list is sorted, and all elements of the empty list, all 0 of them, are greater than or equal to any number. So I'm going to consider this to always be true for every n, and I'm going to name this by sorted empty. Now for the other rule, I'm going to say sorted bounded n. So this is by head cons. So if my list looks like head cons tail, what does it mean for this to be sorted and for every element to be greater than or equal to n? I can say by sorted cons where I need to prove that n is less than or equal to head. And I also need to prove that tail is sorted and every element of tail is greater than or equal to head. So I can say, I can express those two things together by saying sorted bounded head tail. This captures the thing which I've been saying in words. Now, given that I can now say directly what it means for a list to just be sorted, namely, I can prove that a list is sorted. I'm going to say by sorted. By the way, I'm allowed to name a proof rule with the same name as a proposition, so I'll do that here. I can prove this by proving that it's both sorted and all of its elements are greater than or equal to 0, because everything is greater than or equal to 0. So now let me show you, for example, I can prove that the list 1 cons 1 cons 2 cons empty is sorted. I can prove this by sorted, that's this rule. So ask says now I have to prove something sorted bounded with 0 as the bound. Now this list is a cons. It's not the empty list, so I'm going to say by sorted cons. Now ask says I have to prove first of all that 0 is less than or equal to 1, which I can prove by LEZ. And secondly, that 1 cons 2 cons empty is sorted and every element is bigger than or equal to 1. And this still isn't the empty list, so I can go by sorted cons. Now I have to prove that 1 is less than or equal to 1, which I can prove by LESS. And then 0 is less than or equal to 0 by LEZ. And then in this one, I still don't have the empty list, so I have to apply by sorted cons one more time. And now I have to prove, so now the second one is easy. I have to prove that the empty list is sorted, which I can do by sorted empty. And in this one, I have to prove that 1 is less than or equal to 2, which I can say by LESS. And finally, I have to prove that 0 is less than or equal to 1, which I have by LEZ. And now that completes the proof and it changes to proven.